Hello and welcome back. My name is Corey. You're my rubber ducks for the evening. If you don't know what that means, just Google rubber duck debugging. And anyway, this is the series where we are creating a programming language from scratch using our C++ skills and a few tools like Flex and Bison. And the goal for tonight is that we want to use Flex, uh, our Lexer, that is, to process UTF-8 encoded strings. Now, before we get into this too far, I want to make a few clarifications. First of all, Flex is designed so that it only works on ASCII characters. That is, 8-bit characters. And UTF-8 encodings have larger parts. And so what my goal is, okay, so what, right, should always say, well, what are we trying to do with this? Uh, there's multiple ways of solving the problem I'm trying to do. I could use ICU, but I don't want to for a very specific reason. And I should probably go ahead and tell you what I'm trying to do. And that is we are, of course, the essence of what Tang is it's meant to be a template language. That is, the idea is a designer could write a template that when it is executed, it produces HTML. So if there is something that says hello username, it would drop in the username. And of course, it has a lot of other scripting capabilities around that so that you could execute some rather sophisticated code. But for right now, that's what we're doing. That's the goal of this, is to be able to execute a template and the output be valid HTML. And as such, you want to be able to protect the values that are, dare I say, dangerous. And what do I mean by dangerous? Well, values that are usually user provided, right? So in HTML, let's say someone put as their username, fill in the blank, but then they put an HTML tag in there. Or worse yet, some of the early, like MySpace is reaching way back, but they would allow you to include things like style CSS. And in that field, you could actually put in other bits, other things, and they weren't sanitizing the input, and yeah, that's really bad. Anyway, moral of the story: we want to be able to sanitize the output, and we want the output to either be a an HTML escaped string with the most dangerous characters. There's 3 of them that need to be escaped. With those properly escaped, or a full escapement. And what do we mean by that? Well, it's possible to output UTF-8, and you don't have to do anything special for UTF-8 characters. But if you want to represent your UTF-8 document in ASCII, in an HTML document, there are escape codes that are made up of ASCII that you use to identify the different code points. A very good example is, in fact, here, let me just, I can type it out. So one of the ones that you want to encode is the less than. That would be, I believe it's ampersand LT semicolon. Or another one is the ampersand, and that's ampersand AMP semicolon. But if you have a non-breaking space, you can do ampersand in BSP semicolon. And so there are just these codes that ampersand something. I think there's like a U and then numbers, or I don't remember what it is off the top of my head. And that's not the point. The point is that there's ways of doing it. So we have 2 types of HTML escaping that we can do. And one is only escape the most dangerous and leave everything else as raw UTF-8, or the second one is escape everything, and you're left with plain ASCII, but that is it still has all the UTF-8. Excuse me, it still has all the Unicode encodings in there. It's just only using plain ASCII. So those are the two directions we want to solve for. But in order to do that, we have to be able to take a UTF-8 string and break it into its code points and then deal with it. And we could use ICU for that, but I don't want to. I want to use Flex. And part of the reason is just because, well, Flex is another tool I want to get better at using, and Flex is really good at just reading a string. And so that's what we're going to do. We are going to define a set of rules that that will tell us, that we can use to say, this is what is valid, this is what is invalid, and we can make decisions about what to do at those points. All right, so where does this put us at the moment? Well, we have to understand how this works. In fact, let's just go ahead and do a few things. I've said from the beginning, this is 100% live coding, nothing up my sleeves. I don't have anything pre-prepared except for today, and I'll explain that in a moment. But generally speaking, I haven't done any coding ahead of time. And if I say git log, you'll see that the last commit was the end of episode 50, the previous episode. And if I say git status, there's not anything been done to this. And let's see, I know that if I go into Flex, I have this unescape. And what is unescape doing? I don't remember. I just wrote this. Oh, yes. Unescape. I had to look to see what the rules are, recognizing. That's where we have a string, and we want to convert it into a string with all the escape sequences. So we're not escaping the sequences. We are kind of going backwards. So we're unescaping them. Okay. But I am going to copy the unescape, and we're going to call this, like I said, there's two types. There is of HTML encoding. There is the kind of brief, and then there's full. So if we say HTML encode, I don't know. Encode is not the right word. We're escaping it. HTML escape. And full is the full-on one, but I don't want to tackle that right at this moment. But I do want to have, do I want to call it brief? Do I want to call it or just HTML escape? We'll just call it HTML escape. All right. And I think I need to go into my includes and we should have an unescape there. I'm going to copy unescape, and we will call this one what? HTML escape. And now let's edit our makefile and add that. So it's HTML escape. And where is this going to be? After all the computed stuff, so many things. HTML escape. And now we have to add it in the correct places. So oh, and we didn't need these special rules because I had commented them out and it's working. Copying the unescape one, and we'll go back and put it in the HTML escape location. There we go. And 225 to 230. And what are we going to replace? Unescape. We're going to replace that with HTML escape. Okay. And now we're going to go down, and the shared library is going to be compiled into it. But for the Unicode string library, we're going to add it to that. So we've got unescape and Unicode string. Let's do obj_dir. This is going to be HTML escape.o. And do I need to add that here? I do. You know what? Instead of enumerating them, I can just put a caret there, I believe. I guess we're about to find out if I'm right or wrong. Okay. On the right hand side, I'm going to do our make clean, make test, and it's going to, oh, not make test, make test dash watch, and it doesn't know how to make the, Did I forget to do my flex file? I did. And this should be 36 to 40. We're going to substitute an escape for HTML escape. Okay, now it's giving me errors because we haven't changed what's in the flex file, right? We just copied those. So let's edit the flex HTML escape and the source not source, include HTML escape. All right, so we've got this unescape flex flexer. We're going to call this HTML escape flex flexer, and we'll call this HTML escape. Is there anything else? Pound include HTML escape. It's still, I'm going to leave all the rules for the moment. Simple enough. And now we're going to go to this and let's see, %s replace all occurrences of escape, I can't spell, with HTML escape. And we'll do the same thing with the title case. And now let's just make sure that everything is Tang HTML escape flex lexer. I think that's right. HTML escape. All right, so everything compiled, everything ran. And why? Because we basically cloned our unescape flex tool, and it's called HTML escape, but it's still doing the exact same thing that the other one was. Now we get to working with Unicode. And this is where I'm saying I actually did some work ahead of time. I've been trying to put out a video a day, and I had gotten ahead, and so I uploaded videos ahead, and then last week I had a bout of about 5 days where I was trying to track down an issue getting ICU to work how I wanted it to before I recorded my videos. So I wasn't doing encoding on Tang itself. I was doing videos, I was just trying to get it to compile in this ecosystem and making sure I had all the right flags and everything. And my example just wasn't working. Long story short, I found out what was wrong. It was actually working perfectly from the first day, and I was misunderstanding. I was misinterpreting the results. And so, yeah, that kind of threw me behind 5 days. So I got behind a lot of my videos, and because I burned through 5 days where I didn't have any videos. And so I was like, okay, I'm running out of spares. And I thought I'd get ahead again, and so one day I got 2 recordings, like, yay, I'm going to catch up. And then yesterday, what happened yesterday? I decided to do a little bit of prep work on this. Why? Because I needed to read up on the Unicode UTF-8 standard, and then figure out how am I going to approach this with Flex. Yeah. Now you're about to see what it takes, at least to use Flex for just recognizing Unicode strings. Okay, so I have this nice little write-up that I'm probably going to put in somewhere, but we'll go with that in a moment. First of all, let's just jump in. We'll talk about this, and try to make that large enough so it's easy for you to read. If we go to this link, this is the RFC, and I think that this has actually been replaced, but because this is from 03, 20 years almost now, not quite, but almost. And it talks about how UTF-8 works, and I just put it there as a reference. And you can, I guess, read about it on their Wikipedia page. I'm actually looking for something in particular. Maybe they didn't do it in this one. Later they expanded the UTF-8 definition so that it could include more than 4 bytes, and then they did away with that to make it consistent with some other stuff. But this lovely little table is what I have here. I copied it from this original specification. And now let's talk about what UTF-8 is. First of all, it's built on top of ASCII originally. And ASCII, of course, you have 8 bits to work with. Well, originally I guess it was only 7 bits. Well, no, if you want to go into the history of encodings, there's a lot more, and there's other encodings other than ASCII. But ASCII is now, it's kind of like the default. So we don't use some of the other historical encodings unless you are in a very specific environment. And that's not us right now. So it said, you know what? If you are in the first 127 characters of ASCII, then you're fine. And in fact, you can, it's probably ASCII, ASCIItable.com, I think. Yeah. And there you say 127. And then the extended, but we're not including the extended. We're just saying if you're in the first 127, then that's fine. Oh, I don't have an ad blocker on this. Just cover it up. First 127 values of ASCII. Unicode is the exact same as with those. But Unicode, and I've said this before, Unicode is basically a list of this number is this character. And the first 127 are the exact same as the first 127 ASCII codes. And then they define a lot more. Unicode defines a lot more. But how do you then represent those code points when you only have 8 bits? Well, that's what UTF-8 is. It's a way of encoding these code points. And so this is what they do. They say if it's in the first 127 characters, you just use 1 byte, and the first bit, the highest bit, is 0, and then the remaining 7 will encode those 7 bits. Okay, that's fine. What if you need more than 7? Well, it'll spill over into 2 bytes. But it has to follow a very specific pattern. First of all, it now has to start with, instead of 0, it has to start with 110. And then you've got, how many is this? 5 bits to work with. The next byte must start with 10, and then you've got 6 bits. So how many bits total do you have? 6 plus 5. You have 11 bits. So what is that, about 2,000 characters, give or take? 124 times 2, so 2048 that you can encode. So once you get above that point, that again, this is for encoding Unicode. So if you want character number 3, you can use 1 byte to do it. But if you want character number 1,500, you're going to have to use 2 bytes, and you split up the bits in this way. Okay, so if you need a number above that, you can expand it out to 3 bytes. And again, it's the same problem. Excuse me, it's the same issue. You get 6 bits, 6 bits, and 4 bits. And then, or if it's a really big number, 6 bits, 6 bits, 6 bits, 3 bits. So that's a total of 21 bits. And 21 bits is currently, that is large enough to represent everything that is, I think it's everything that's defined. That might not be quite the right wording. But like I said, they used to have another encoding that was, 5 bits. And it followed this pattern. And you got 2 bits there. And then you could have, what is this? 6? Yeah. 2 bits there, and then 6, 6, 6, and 6. So 24, 25, 26 bits. Anyway, we don't have that anymore. We don't need it. So, okay, so this is what I started at. And I've got a couple of observations. Values 0 through 7f. That's the largest that 7f is the largest that you can describe in 7 bits. 1 byte, and then I've got the ranges. Add 1 to 7f and you get 80, all the way up to 7ff. Yeah, so these are your ranges of values. Now, 10FFFF is not the largest number that will fit in those 21 bits. But we'll get to that. Okay, so just first of all, so that you understand, UTF-8 is a way of describing which code point you want. And it just so happens that they intentionally chose it so that ASCII UTF-8, a UTF-8 encoding of ASCII looks like ASCII. And if all that you see is a bunch of ASCII characters, you can't tell if this was intended to be an ASCII encoded sequence or a UTF-8 encoded sequence because they are identical. Okay. Okay, so if we see that, then let's just see the largest Unicode valid is defined as this 10FFFF. And so I took that sequence here, that's the same sequence up there, and I filled in, here's the 10, excuse me, this is the 1, though that's the 0, that's why I have this down here, the 0, and then F, 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 F. I mean, yeah, there. Now, but why do I have this F4, 8F, BF, BF? Because when we talk about 10FFFF, we're talking about the bits that had been spread across these other bits. But once you spread out the bits into the 21 available spaces, these are bytes in and of themselves. And if I translate that into Unicode, into just hex values, I get all ones, that's an F, 0100, that's a 4, 1000, that's an 8, here's an F, and so on and so forth. So in other words, that is the largest legal Unicode value at the current definition. All right. That means there could be something larger than that. If this number right here is add 1 to it. And you say, well, and yeah, even leave the 10 there, and add 1 to this, followed by that, followed by that, followed by that. There's room to put data in there. And so we say we could encode a larger number, but it is not valid Unicode. Okay? That's what we want. Okay, now there's another issue called surrogate pairs. What are surrogate pairs? Well, it has to do with something in UTF-16. And I could go into it. I don't want to. But all that you need to know about surrogate pairs is that it is a section of Unicode code points. Remember, code points are 0, 1, 2, 3, 4, right? The first 127 are ASCII characters, but all those are code points. There is a range of Unicode code points that Unicode says you cannot use these because it means something different in UTF-16, and we want UTF-8 to match it. So you know what? We're just going to say you cannot use these code points. And that is the code points D800 or D800 through DFFF. As it so happens, they only occur in the 3-byte sequence. But that means I don't have this lined up correctly. There we go. Now it's lined up correctly. This means that if you have a value that is in between that, it's an invalid code point, and you should do something about it. Well, depending on what our program is trying to do, but we have to account for it. All right. So we've got the fact that we could have, as we're looking through text, it can be 1 byte long, 2 bytes long, 3 bytes long, or 4 bytes long. We've got the fact that it can't be too big. We've got the fact that there are valid encodings of numbers that are not valid UTF-8 code points. And then we've got another problem, something called overlongs. What's an overlong? Well, let's just say this. Let's say we've got the number, the code point 0, ASCII value 0, a null character, right? How do you represent that in UTF-8? Well, 1 byte, all zeros. That fits the pattern of the first bit is 0, and then the rest of the bits are how you encode the number, but since it's 0, they're all zeros. But you could encode it as a 2-byte sequence in this way, or a 3-byte sequence like this, or a 4-byte sequence. That means there's 4 different ways to encode a 0. Unicode, the UTF-8 standard says, nope, we're not going to allow the longer versions. You must use the shortest number of characters possible. And in so doing, all of the remaining ones that are too long are called overlongs. That's this right here. They're called overlong. And so even though this fits a valid UTF-8 encoding pattern for a 2-byte sequence, we have to discard any values below, and I'm going to go back up to the top, a 2-byte sequence, any value that is less than 80. Likewise, for a 3-byte sequence, if there is a value encoded that is less than 800, or for a 4-byte sequence, if there is a value that is less than 10000. I know 10,000, but it's in hex, you know. We have to discard that. And now you got to think about, well, wait, we're dealing with flex, and all that flex can do is it can use a regular expression to identify a byte. And it can do a byte range, meaning like A to Z, or we can specify the hexadecimal value. But what's proper and what's not. And by the way, this is why I said I didn't get to record a video yesterday, because I was writing all of this out so that I could explain it to you. So here we go. First of all, if we're trying to enumerate the valid and invalid states. So for 1 byte that fits this pattern, 0, what is valid and what's invalid? Well, this one is the simplest. If it's a 00, these are hexadecimal values, 00 through 7F, it is valid. If it starts with 80 to BF, that means it 80 to BF all start with 10. It's invalid. That character itself is invalid if it's the first byte. You go back, look, and you'll see in these encodings, you cannot have something that is a 10. That is specifically one of the, that might be an easier place to point it out. That is one of the follow-up tags. So, what I was saying, yes, there we go. So 80 to BF is invalid because it is a it should be one of the subsequent tags. What if it's F8 through FF? Well, that gets into where the number is too big. And what is that? That is, again, if we go to, where's the 4-byte encoding? I'm going to scroll up. Yeah, the 4-byte encoding. If this is, you know what? I can do the calculator. There we go. This first digit, I'm going to type this in binary. 1111 0111. That is the largest value I can fit, and it is in hex F7. If I add 1 to that, I get F8. And so, if I scroll down, F8 and bigger is definitely invalid for the first byte. If I have an F8, that would mean it's 1111 and something else. You know, it does F8 through FF. You know, these last three are going to last 3 bits are going to be different values of zeros and ones, but this will be a 1. So that's invalid. Okay, now I'm going to go through these a little faster. You may have noticed that C0 to F7 aren't listed. It should go right here, right? If we're going in order, there's a space here. In fact, maybe I'll just move this up there. Why are we skipping it? Because those are covered in the rules below. All right, so what if we have 2 bytes? And that follows this pattern here. And what are the valid ranges? C0 through DF and 80 through BF. And that is all of the valid numbers. But I say we can't have an overlong in there. What's an overlong? That means we're encoding a number that's in the previous range. So this pattern, C0 to C1 and 80 to BF, is definitely invalid because it's overlong. So even though it fits the pattern, the number that it's encoding is too small. It's an invalid UTF-8. All right, what about this here? This is invalid. Excuse me. This is valid. It's in the range. So this is almost the simplest, right? That we have the overlongs and then we have all the valid ones after it. Now, in the case of one of these others, the first byte is valid, but the second byte, look, it's either starting with a 0 or it's starting with a C in hex. Where's my calculator? It's 1 1. Let's just clear this and I'll type a C and you'll see in binary it's 1 1 0 0. So the point is that it's the second right here. The second byte cannot start with 1 1. So anything starting with 1 1, that's C and above, is invalid. Now the question is what do we do when we get an invalid character? Well, according to the specification, we pretend we didn't see that one yet. And we just stop after the first byte and say it's invalid, and we start off on the next byte as a new character. That is the recommended way for dealing with Unicode. Okay. So we've got those 2 rules. What about the 3-byte ones? Well, this is our accepted range, but even if it matches that pattern, first of all, we can't have overlong, so we can't have a smaller number encoded, and we have to worry about the surrogate pairs. Here are the 6 rules that determine this. Byte 1, just E0, byte 2, this range, and byte 3. If it matches this, then it's invalid because it's an overlong. And then we've got 3 rules that match valid ranges. Why can't we combine them? Because this one starts at A0, whereas that one starts at 8O. This one only goes up to 9F instead of BF. So yeah. But these are the valid ones. And then we get into the surrogates that are, remember, they have an overlap with UTF-16, so Unicode says you can't use these. So we have to recognize that we encountered it and it is an invalid code point. All right. And then we've got more valids after the surrogates. And then we've got to worry about, what if I have the bytes that would start a 3-byte sequence and then I've got an invalid second byte. So the first byte is a valid start to a 3-byte sequence, but the second byte is just wrong. Well, I have to take the first byte and say it's invalid and then start fresh on the second byte. Likewise, what if the first 2 bytes are valid and the third one is wrong? I have to account for that. Okay, 4 bytes. There you go. First of all, we have to account for the overlongs. Then we've got 3 rules for all the valids. And then we have rules for it's a valid sequence, but the number is too high, so it's an invalid code point. And then we've got all the rules for dealing with, these 2 are dealing with the first byte is good, but the second one is broken. These 2 are, don't mean to drag. The first byte is good, the second byte is good, but the third one is incorrect. And this one is the first byte is good, the second byte is good, the third byte is good, but the fourth one is incorrect. So these are all this kind of different rules. And that, oh yeah, the errors, and I even have a thing about chapter 3. I've got a link to the PDF about Unicode recommends providing a replacement character when encountering an error. But the error should end as soon as the invalid character is found. So yeah, and that's what I talked about. So the whole point of this, and I haven't even gotten to any coding yet. This is why I think it took about 4 hours yesterday. But anyway, writing all this out and making sure I didn't make a mistake. Oh boy. Yeah. Rules for 1 byte, 2 bytes. And by the way, if you now look, C0 through F7, that's what's going to be the start of all of these rules, all the way up through F7. And anything larger than F7 is definitely too large. It's not defined by the UTF-8 encoding, and so therefore it is an invalid. I don't have to worry about what's after it. It's just that is invalid as it is. Okay. How do we convert this so Flex can read it? That's these rules right here. First of all, I have, I'm calling something valid byte, and it's just a pattern I can refer to because it's used a lot. It's not even any shorter. In fact, if I put them one on top of another, yeah, they're almost the same size. So it's not about being shorter. It's about the fact that it gives meaning to this. 80 through BF are all of the characters that can fit into this pattern. Okay? And we use that a lot. 80 to BF, 80 to BF, 80 to BF, 80 to BF, 80 to BF. Sometimes for detecting valid, I should have highlighted the valid ranges, sometimes invalids. But why do we say it's a valid byte? Because it's a valid UTF-8 encoding. Whether or not The point that it's encoding is valid. That's another story. But the byte itself is a valid byte. Okay, so I've got this little helper function. And what I did is I went through and for each one of these, 00 to 7F is valid. 00, that means hexadecimal 00 to hexadecimal 7F, it's valid. I haven't written what I'm going to do yet because that wasn't the point. The point was to just start enumerating all these. If I have a valid byte here, it may sound confusing, it's invalid, but it's because this represents something that must be in the subsequent bytes, not in the first byte. So I've got that as a thing. And you know what? I should probably use lowercase 6x's because that's consistent with the other stuff above. And this one is the range F8 through FF. And I went through for each one of these. These are all of the 2-byte sequences. Excuse me, the 2-byte sequence, I've got an invalid and a valid, and then the incomplete where I'm not reading the second byte. And the reason this works is because what Flex does is it tries to match the longest pattern that it can. If it can match a valid byte, it will. But if it matches the first byte and then the second one isn't valid, it will only match this one, and I'll know, hey, this was invalid, and it will pick up where it left off on that next byte for the next pattern. All right. That was our 2-byte ones. Here are the 3-byte ones. That list. I'm going to zoom out just a little bit so it'll all fit on the same screen. These are the 3-byte ones. And notice I've got them all listed out. The overlong, which is invalid. The valid 3 bytes, valid 3 bytes, valid 3 bytes. The surrogate, valid 3 bytes. The incomplete, or invalid because it's incomplete, invalid because it's incomplete. And you can go and you'll find that it matches each one of these. Nope, didn't mean to drag. Each one of these rules. Okay? And then we'll go down, and then the 4-byte ones. I have to zoom out a little more. But these are the 4-byte rules. All right. What are we going to do with this? I'm glad you asked. I should probably put all of this into a help file or a README. And in fact, guess what I'm about to do? I'm going to, for the moment, I'm going to edit a file in flex slash, do I want to call it README or should I call it UTF-8 UTF-8 flex regex.txt. Okay. And I'm just copying and pasting. And that is my brain dump of this. Please forgive me for having worked on it off camera. Now, I'm in. That goes down to 124. So if I start here 63 to 124. What is that? 60. I'm going to delete 60 lines. There we go. Now, I believe... Ooh, I'm old and forgetful. I guess we're about to figure this out. That my valid byte thing, my rule, needs to go right there. And now I need all of these rules to go right there. Say, Corey, I can't believe you're just copying and pasting. I know. I feel dirty about it too. My apologies. Let's just make this do something. What I'm going to do is I'm going to say return YY text. So if it's valid, just return YY text. And we are actually just going to return YY text in the case of every single thing. There. Get everything on the screen. All right, now I'm scrolling up because I want HTML escape. Notice, there we go. HTML escape, it didn't give me any warnings. I've taken into account every single possible character pattern without having to have the dot character. What should happen now is that it should be a pass-through. That is, whatever I feed into it, because in every case I said valid or invalid, just return it. All right, so we want to edit now our include for Unicode string. And we've got this unescape. And let's add a HTML escape. Return an escaped version of some people would say a HTML. It's like, no. I pronounce this letter, that letter right there, as H, and so it sounds right for me to say an H. So return an HTML escaped. Version of the provided string, which when interpreted by Tang should result nope, so I was like, why is it not giving me the I had set no paste or set paste so I could copy and paste earlier without it messing up the indentation. I had to turn that off. Now it's working. All right, so what are we going to say? Only critical characters less than, greater than, and ampersand will be escaped. You say, Corey, why'd you go through all this work? Trust me, we will need it. But for right now, we're going to say this. Only these three will be escaped. All other characters will be allowed through unaltered. The result is a UTF-8 encoded string that is safe now. The question is, should we also do the double quote? I'll think about it. That is safe for inclusion in an HTML template without disturbing the HTML structure. I think that we should also do the double quote and the single quote. This is just, it's a memory that I have of, oh no, these should also be escaped, and I don't remember why. Okay, so I'm telling you up front, I don't have a good reason for this other than something in the back of my head is telling me that it needs to be done. That's usually not a good way of writing your standards, but okay. So I've got this HTML escape and this thing to be escaped, return. So this is an escaped version of the provided string. All right. We need to add this. So our HTML escape. And to do that, we're editing the source for Unicode string.cpp and not grapheme offsets. Let's copy the unescape and we will call this HTML escape, and HTML escape there, we'll call it H. If I just save this, will it, oh, H was not declared in this scope. Yes, it was. Oh, HTML escape, it was probably not. I didn't include the pound include. let's do a test. We're going to write a test, and let's do a Unicode string. That's because that's where this is. We've got the unescape. We're going to just copy this. And the empty should be empty. You know what? We're going to, so this is 32 through 49. 32 to 49. What are we doing? We're substituting an escape for HTML escape. Oh, and we need to rename this. And none of this is right. Well, actually, that is not true. It did a pass through. So the first one that's wrong is line 35, and which one is line 35? So all of these. The question is why? Oh, because we said that these were raw strings. And if we, for the moment, even though null is not a valid Unicode string, I don't think, but that one doesn't need to be there. In fact, yeah. There, it's gone. And now we also need to do the same thing here. X. Okay, all tests are passing. They shouldn't be. Why? Because that one should be ampersand less than. In fact, oh, where are you? Didn't I just... HTML escape sequences, there should be... You know what, that works. How many of these are we doing? 1, 2, 3, 4, 5. So this should be greater than ampersand GT. An ampersand should be ampersand AMP semicolon. Single quote should be ampersand QOT, and a single apostrophe should be ampersand APOS. And these should all fail. They do. Good. Now what we're going to do is we're going to go back to our flex file and now say, well, what are we doing? Right now we're passing through everything, and you may think that this is really, yes, you're right, we could have condensed this down. But I wanted first of all, the experience of working with flex here, and second, what we will need for later is definitely going to be worth the work. So what we're going to say is if text sub-0 is double equal to something, then return something else. Okay? And this is going to be match the 5 characters that we want to protect against. That we want to, how about just escape? Three, 4, 5. There we go. So the first one, if it is a less than, return ampersand, ampersand, there we go, LT semicolon. If it is greater than, return ampersand, greater than, semicolon. If it is an ampersand, return ampersand AMP, semicolon. If it is a single quote, then return ampersand QOT, semicolon. And if it is I had to use a slash for that one to escape it. Where's the ampersand? It's above the 7. Yeah. APOS, semicolon. Now, a different test should fail. Oh, whoops. It would be nice if I typed the right thing. There we go. We still have a failing test, but we're about to fix that. All right. Now, what it is we ran the so our test, let me just bring that up. Our test here, we're testing single characters, and I just wanted to make sure that everything passed through, even, weird stuff. I don't have multi-byte stuff in here yet. In fact, I could grab one. What's... should be the same. Oh. There. And that one passed, by the way. Here, I'll show you. Put a space in there, resave it. Yeah, it failed now. So, again, it works for multi-bytes. But we're not escaping anything. I mean, everything's just passing through. The problem is this one right here. All the letters, and then this right here, ampersand, should be AMP semicolon. Single quote should be ampersand AMP semicolon. This one should be ampersand LT semicolon. This one should be ampersand GT semicolon. What am I forgetting? I'm forgetting the single quote, which is ampersand QOT semicolon. Not ampersand. Well, not percent. Ampersand QOT. There. Oops, forgot. And I need to add the double quote there. That means I forgot to include it down here as well. Whoa. Wherever that's supposed to be, first of all. There. All right, I'm back, and evidently my software crashed. And I didn't, thankfully, I think I've only lost like about 2 or 3 minutes. All that I had done is, and I don't know if you saw this or not, but I had one or two, no. Down here, I had 1 or 2 extra lines. Like I had 2 of these. And I deleted one, and as I was looking through, and I copied like this Unicode, this Unicode string line, and just as a test to HTML escape it, and everything, I'll put it up here, and everything came through unscathed, which is what I wanted. And then in my big HTML escape thing, I filled those in. I think you saw that. And then on this line right here, I fixed all the problems. There was a missing double quote, and now they are all actually included. Yeah. And this, again, just shows that it will process multiple things. And if I hit save, all my tests are still passing, and that's a good thing. So, moral of the story. What do we have here? We have an escape function that doesn't do much. In fact, you may say it's overcomplicated and over-engineered. And I would say, yeah, you're right. But, and again, I'm kind of worried now since my program has already crashed once, to go too much longer. But what we've got, or what we have in the regex, is now we've got a tool that we can use to build a full HTML escape. And what do I mean by that? Well, if I pull up, get rid of all of those, and just say HTML escape codes, we can I could have sworn that there was one on Wikipedia. It's not here. Oh, right here. Yeah. Oh, that's why I was saying I'm pretty sure there's the apostrophe and the double quote, but that's the QOT semicolon. Let me make this larger. Why? You have too much money as it is. Yeah. So there's these that we just used, but there's actually, can you see how small the scroll bar is on the left-hand side? Each one of these, the pound sign can be included as ampersand, NUM, semicolon. The percent, ampersand, PERCNT, semicolon. And it goes down through all of these different characters. There's one, you know? That one has two possible encodings. And again, why would you do something like this? Well, remember, right now we're using UTF-8 encoded strings. But what if you can only use ASCII encodings? Well, that's what this is doing. It changes every single code point into an ASCII compatible encoding. And you say, does it have something for every single code point? No, it has about 1,500 of them, maybe 1,800. And then for things outside of that, you can use something like this, or the hexadecimal representation. That's what we are going to be doing next, because we've got, like I said, what we just wrote is an escape function that only escapes the absolute necessary so that it can leave things in a UTF-8 encoding for space reasons. But if you absolutely can't use UTF-8 and you need everything ASCII encoded, but you wanted you still want all of the Unicode characters, that's what you need the full encoding for. And that's what we needed all of those regular expressions for, so that we can write rules when we've got a 4-byte character and it's valid. Let's figure out what it belongs to. Or if it's invalid, what do we do? Well, that's the replacement character. In fact, Unicode replacement character. Yeah, you replace it with this when you have a problem. So, yeah, that's what we'll be doing. But we had to have all of that work done. And, all right, let's clean up a little. There's one thing what has changed in this? Which file am I in? I'm in HTML escape. Well, I'm wondering if something happened in the... Okay. There. So I should be able to close that. And, you know, let's just see, get status. No, don't do that yet. and this is going to be add HTML escape class and HTML escape function to Unicode string library. Library? Sure. All right, now there's one other thing that I didn't like about this last thing that we had done, and that was with pretty sure oh, there's going to be a lot of binary file matches. Let's do that. Let's just go into the source and rerun that. And well, that's not good. What was this in? I'm trying to remember what it was. One moment. Was it in the unescape? Yes. The unescape formatting in the computed expression string as code. But the unescape, that's what I want. So, oh, and that's why it wasn't showing up, because I think it's in the flex stuff. So flex, no, I'm in the wrong, there we go. Flex unescape. And what I'm looking for, I saw this when I was editing the video and I didn't like the way it looked. This right here. YY text, and I'm doing a bitwise and I'm taking 15, which is 0xf, right? The 4 lowest bits, and I'm shifting them up 4, doing a bitwise and then shifting the results down 4. That's stupid. This is a char. All that I need to do is shift it down 4, and it will zero fill the uppermost. And now I'm going to save this. All my tests should still pass, and I will have simplified a line of code. Or not. Well, this is right, but what I should have done is let me undo this just for a moment. Okay, so what's the problem? I'm actually, no, that should have worked. What am I overlooking? CH is a char. You can't get the highest bit if it thinks if it's a negative number. So if I say unsigned char or uint8t, that's an unsigned char, can I do this here as well? uint8t, that way I don't have to cast it. Oh yeah. This will work. We'll give it just a second. For the moment, well, okay, just to play nice, we'll say char buff, and I'm going to convert this to a uint8t, while I text, shift it left by 4. It should like that now. All tests are passing. So what did I do? I said ch is an unsigned int of size 8. Why did I have to say unsigned? Because if it were signed, then ch, when it's those high numbers like A, 1010, for the high 4 bits, it thinks it's a negative number. Anyway, and those don't work like you think they're going to when you do shift right and shift left. So I'm telling it here that, you know what, YY text sub-0, the first character, treat it like an unsigned char, and just now take that unsigned char and shift it right 4 bits. And that'll give me the top 4 bits of it. And now I can do my comparison and say the character is equal to, is it 9? So I could simplify this further by saying buff2 is equal to that, and buff3 is equal to that. Again, just simplifying. I don't have to do that there, but it makes me feel better. It's symmetric in the code. There. A little bit of space to make things more readable. So the upper 4 bits, ch is equal to the upper 4 bits, and then if it's set buff2 to be this computation, ch is the lower 4 bits, and set it to be that computation. All of our tests pass. We're good. That's why we have unit tests. Let's just exactly what I expected it to be. So git commit and just say simplify logic for hexadecimal values. Sure. Now, let's wrap all this up. Make docs PDF. What episode are we on? Episode 51. Okay, so update the docs for episode 51. Push everything up. 051. The message will be the same. Episode 051. And episode 051. All right. One of the last things we do, okay, we're getting there. When we do the second version, realize this, when we do the second version of the HTML thing where it's got some 1,500 lines, oh yeah. And that is something I probably will start preparing off screen just so you don't see me type out 1,500 lines. No, I will probably write a small program that will generate it based off of the data from Wikipedia or something. But that will be coming up next. And then what will we do? Well, we need to incorporate this into our programming language. So for the next video, I'm not sure if we're going to do the incorporation yet, or if that's going to have to be a third video, but we'll just see how it goes. For right now, I need to go back and figure out how much recording time I lost to be sure. So yeah, as always, I hope it's been useful to you, and so hopefully the information is good, even if it's just about learning about UTF-8 and Flex. So thank you, and have a great day.